Imagine this: particles that behave like ghosts until you look at them, reality that doesn't settle until someone hits observe, and objects separated by light years acting like they're connected by invisible threads. This isn't sci-fi. It's quantum physics. It's strange, it's confusing, and it's real. From the chips inside your phone to the fusion inside stars, it's the invisible engine powering our universe. This video is all you need to understand the key concepts of quantum physics, explained visually, simply, and without overwhelming math. Let's dive into the science that rewrites the rules of reality. In the quantum world, things aren't just one thing. They're two things at once. Light behaves like a wave, spreading through space, bending around corners, interfering with itself like ripples on water. But look closer, and it's made of individual particles called photons. Same with electrons. In the famous double-slit experiment, electrons fired at a barrier with two slits create a wavy interference pattern, like water. But when we try to observe which slit they go through, the wave vanishes. They act like particles again. It's as if reality chooses a form based on whether we're watching or not. Wave-particle duality tells us that even the smallest pieces of the universe are undecided. It challenges our classical view of cause and effect. It's like someone who performs differently based on who's watching. The universe is reactive. Superposition is the idea that a quantum object can be in multiple states at the same time. An electron doesn't choose left or right. It's both. It doesn't spin up or spin down. It spins both ways until measured. This isn't just theory. In quantum computers, qubits hold a 0 and 1 at once, vastly increasing power. Think of it like standing at a crossroads and going in every direction simultaneously. You only choose a path when someone checks where you went. It's the logic behind Schrödinger's cat. Alive and dead in a sealed box until someone opens it. Superposition isn't about indecision, it's about every decision. In classical physics, you can know where something is and how fast it's moving, no problem. But in quantum mechanics, not so easy. Heisenberg's uncertainty principle says, the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. It's not a limitation of our tools, it's baked into nature itself. Imagine trying to take a perfect photo of a moving fan blade. You can freeze the blade but blur the speed, or track the speed and lose the sharp image. The act of observing disturbs the system. It's like poking a balloon to check its pressure. Your poke changes the very thing you're trying to measure. This principle reminds us, in the quantum world, the act of measuring isn't passive, it's invasive. Entanglement sounds like magic. Two particles become linked so deeply that what happens to one instantly affects the other, no matter the distance. It's like having two playing cards, one in New York, one in Tokyo, and when you flip one, the other flips too, instantly, without any signal. Einstein hated it. He called it spooky action at a distance. But the experiments proved him wrong. We don't know how it works, but we know that it works. Entanglement is already being used in quantum encryption and teleportation labs. It opens the door to communication that's secure and possibly faster than light. The universe might be far more connected than space itself can explain. In our everyday world, if you don't have enough energy to climb a hill, you stop. But quantum particles don't play by that rule. They can tunnel through barriers as if by magic, even when classical physics says they shouldn't. It's not cheating, it's probability. The wave function of the particle has a chance, however small, to be on the other side. Imagine walking into a wall and occasionally just phasing through it. In quantum mechanics, that's not absurd. It's expected. Quantum tunneling makes fusion possible in stars. It's also what powers technologies like flash memory and STM microscopes. It proves that in the quantum world, barriers are suggestions. Every physical theory needs a backbone. For quantum physics, that's the Schrödinger equation. It doesn't give you the location of a particle. It gives you its wave function, a map of probabilities. It tells you where the particle is likely to be. Think of it like a weather forecast. You don't get rain at 3:07 p.m. You get a 70% chance of rain. That's how particles behave, through likelihood, not certainty. This equation helps scientists predict how systems evolve over time. It's what makes quantum mechanics work, and what lets quantum models be applied to chemistry, electronics, and more. Even though it's invisible to most of us, this equation shapes everything from atoms to devices in your hand. In classical physics, energy can take on any value, but quantum mechanics says, nope, only certain amounts are allowed. This is quantization. Energy, charge, and angular momentum exist in discrete units, no in-betweens. Imagine a staircase. You can stand on one step or the next, but not float halfway. That's how electrons behave in atoms. When they jump from one energy level to another, they absorb or emit energy in exact amounts, and that gives rise to everything from the colors in fireworks to the light in lasers. Quantization explains the precision of atomic clocks, the glow of neon signs, and the structure of the periodic table. Quantum physics isn't just weird theory. It's the foundation of modern tech. Lasers, semiconductors, MRI machines, solar panels, LED lights, quantum tunneling in flash drives. It's all quantum. GPS satellites adjust for quantum time shifts. Quantum computers promise breakthroughs in chemistry, medicine, and AI. Even the device you're watching this on only exists because quantum mechanics makes it possible. Understanding quantum physics doesn't just explain the universe, it powers the future. So next time you look at your phone, think about the particles behaving like waves, the states collapsing, and the universe watching itself through you. Quantum physics isn't just hard science, it's a glimpse into the nature of reality. If you learned something new today, like and share. There's so much more to explore.